All right, now in this part of it, part two of the chapter is about reactions. Okay, and the interesting thing about this is that the mechanism is exactly the same throughout the whole entire chapter. So if you really understand the mechanism, you'll pick up all these reactions. It's going to seem like a lot of reactions, but it's really not. All right, and it's basically called a nucleophilic acyl substitution, means you're substituting the acyl group, the group that's attached to the acyl, with a nucleophile. Okay, so interconversion of acid derivatives occurs through this nucleophilic acyl substitution. It adds to the carbonyl, forming a tetrahedral intermediate. Then the negative on the oxygen pops back down, eliminating a leaving group, generating the carbonyl and whatever nucleophile you just added to it. All right, it's an addition-elimination mechanism. Nucleophilic acyl substitutions are also called acyl transfer reactions because they transfer the acyl group to the attacking nucleophile. So, a lot of words. Here it is in picture form. All right, very simple. You have a nucleophile, which is coming into your carbon, because remember, that's partial positive. Now, Y is your leaving group, and it all depends on the derivative. It could be a chlorine here if it's an acid chloride. It could be a carboxylate group for an ester. It could be a alkoxide group if it's a ester. I'm sorry. The previous example was a carboxylate group for an anhydride, not an ester, anhydride. Alkoxide for an ester, or an OH for carboxylic acid, or a triple bond N for nitrile. By changing the different group, you're changing the Y, you're changing the leaving group ability, right? Chlorine is the best leaving group. So if you had a chlorine here, you would have the most reactive compound, okay? So, but it's not really important. This is just the general mechanism, and if you understand this mechanism, you understand pretty much every reaction in this whole entire chapter. Okay, so nucleophile comes up, you form your nucleophilic substitution, your tetrahedral intermediate, your negative pops down, kicking out your Y group, and you have just substituted your acyl group with a nucleophile. That's the mechanism. You understand it? You're good to go. Okay, so here's even the hint. This mechanism applies to most reactions in the chapter. Now, as far as reactivity, okay, this is what we've talked about before. The acid chloride is the most reactive. The carboxylate, or the anhydride, is the next reactive. Then the ester, then the amide, then a carboxylate group is really not reactive because you have a negative. Okay, and again, remember, leaving group ability depends on how strong of a base. The weaker the base, the better the leaving group. The stronger the base, the worse the leaving group. Okay, so amides are really poor leaving groups. Amides are very stable, which is good because our bodies are basically made of amides. Okay, all of our proteins, okay, everything, okay, our skin. If our skin were acid chlorides, as soon as you took your very first shower or bath, you would completely all dissolve and you'd be a big puddle of slime on the ground. Okay, so it's a good thing we're made of amides because the amides are very non-reactive. Okay, so acid chlorides are the most reactive, followed by the anhydrides, followed by the ester, the amide, and like the carboxylic acid. I love this diagram. This diagram is kind of something that you should make on your own and fill in all of the reagents. Think of this as a carboxylic acid, not a carboxylate. I don't know why they do that. But this pretty much shows you how you can make everything from all the compounds. So it kind of shows you, first of all, actually, let me go back to this. The reason why we're looking at the reactivity is because an acid chloride can make everything underneath it on the scale. So acid chloride can make an anhydride. You can take an acid chloride and make an ester. You can take an acid chloride and make an amide. You can take an acid chloride and make a carboxylic acid. Now let's look at the anhydride. Anhydride can make an ester, can make an amide, can make a carboxylic acid. Anhydrides cannot make carboxylic acids. Esters can make amides and carboxylic acids, so forth and so on. Okay, so that's kind of what this is showing you. It's showing you that the acid chloride can make the anhydride, see the arrow, anhydride, the ester, the amide, the carboxylic acid. The anhydride can make an ester, an amide, carboxylic acid. The ester can make an amide, there's the arrow, amide, can make a carboxylic acid. And the amide can just make a carboxylic acid. However, the carboxylic acid makes the acid chloride by SOCl2. Now, you can also make an ester from a carboxylic acid. How do you do that? The Fischer esterification. You can make an amide. So acid chlorides and carboxylic acids can actually make everything. But this is kind of a neat type of a diagram, because what you basically do is, how do you think you go from an acid chloride to an ester? Okay, remember the mechanism, acyl substitution. If you want to substitute this chlorine for this group, well, what do you think you add to the acid chloride to make this? You just add that group. So you add O negative carbonyl R. Okay, so that's basically what will go in this arrow. You add this to the acid chloride, you make the anhydride. If you want to make the ester, what do you add? RO minus. If you want to make the amide, NH2 minus, the strong nucleophile. If you want to make carboxylic acid, hydroxide. That's basically it, guys. That's the whole chapter. Okay, so how do you think you go from an anhydride to an ester? Well, you're substituting this whole thing for OR group. So if you want an OR group there, add RO minus. You want the NH2 there, add NH2 minus. Okay, and so forth and so on. Okay, so there's how many reactions here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 or 10 reactions, and they're basically all exactly the same. Okay, so I pretty much have showed you 80% of this chapter already. Okay, the more reactive derivatives can be converted to the less reactive derivatives. Pretty straightforward. Here's a mechanism. Okay, you want to turn the acid chloride to the anhydride. How do you do it? You can either add the carboxylic acid, or you could also add the strong version of it. It doesn't have to be the weak version. So one of these, if you do the weak, okay, here's the mechanism. Tetrahedral intermediate pops down the chlorine deprotonates to form your anhydride. If you don't have if you just have the minus, then you don't have to worry about the proton transfer step. Okay, if you want, we can go over that mechanism in class. But why don't you see if you can figure it out? It's actually a much easier mechanism than the one that's shown here. Okay, so there you go. That's to the anhydride. Acid chlorides, the esters. Just like I said, ROH, or you can add RO minus. All right. Again, do the one with the RO minus, and the mechanism is a lot easier. Same thing. Okay. So all we're doing is going down that list that we looked at. Acid chloride plus an amine gives you the amide. Okay. Now here's anhydrides to esters. What do? You just, whatever group, again, whatever group you have here, you just add that functional group. If you want an RO, add RO with an H there, or add RO minus. Okay, and that's all like the next, I don't know, 20 slides are. That's why I'm going to go kind of quick, because you know how to do this. There isn't, at this point, you should be like, oh, this is pretty straightforward. It all comes from that slide I showed you. Try to keep that slide in mind. This slide, if you want, maybe you should print this slide out and always have it next to you, because that's basically what we're going over. Okay, right now, so the past 4 slides we're going over this acid chloride to the anhydride, to the ester, to the amide, to the carboxylic acid. Now we're going from the anhydride to the ester, to the amide, to the carboxylic acid. And I'm sure the slides after that is ester to the amide, and so forth and so on. So let's get back to where we were. We were at anhydrides. There's the alcohol. Here's the amine to make the amide. Okay. This is a primary amine. You can do it in secondaries. All right. Here's showing a mechanism. Okay. Oh, this is now the ester. Sorry. Now we've gone to the ester. Okay. There's the ester plus the amine. Esters only make the amides. All right. All right. So the amide makes the tetrahedral intermediate, pops down the O negative to make an RO minus, which then deprotonates your hydrogen. Okay. Leaving groups in nucleophilic. Yep, just talking about the RO minus is the leaving group. You have a strong base, which deprotonates. But yeah, so okay. So notice it's not usually a leaving group. RO minus is not a good leaving group. Okay, but this reaction is exothermic. Why is it exothermic? Because this your product is so much more stable than the ester. Okay. So you have something, if you look at an energy profile, you have your starting material ester right here. The reaction, your product is so much more stable, you have an exothermic reaction. So that's the driving force of the reaction. Okay, now this is kind of a side trip. Okay, transesterification. What's transesterification? It's where you have an ester, okay? And you basically want to change the R group on your ester to a different R group, okay? It's basically, you know, you're swapping out one alcohol for a different alcohol. So you just add this alcohol in huge excess, heat it up. The mechanism, again, what do you think the mechanism is? Okay, if you're in acid, you're going to protonate first, then your alcohol is going to come in and do make a tetrahedral intermediate, and you have an ORO as a leaving group. Here's the mechanism. Okay, first step, protonation. Okay, protonated the carbon, alcohol attacks, kicks up your pi bond, tetrahedral intermediate. Okay, what I like to do is I like to just have this grab the proton. It saves a step for the proton transfer to form that intermediate, so you can go straight to that compound. Pops down, kicks out the alcohol, and then you deprotonate. Here's base-catalyzed. You save a lot of steps. You don't have to protonate. You have an O-. It immediately attacks, forms an O-, pops down, kicks out your original RO- group. Hydrolysis of acid chlorides. Right? Hydrolysis, it might be a term you've used or heard before. Hydrolysis just basically means broken down with water. You're breaking down some compound with water. Okay, and that's what you're doing. You're basically taking water, you're adding this, and you're breaking down your acid chloride to a carboxylic acid. Okay, same thing. Nucleophile adds, kicks up the pi bond, kicks out, chlorine kicks out, grabs a hydrogen, HCl. These mechanisms are the same thing over and over and over again. Okay, hydrolysis occurs quickly, even in moist air with no acid or base catalyst. This is on acid chlorides. Okay, it should say hydrolysis of acid chlorides occurs quickly, even in moist air. Acid chlorides are very reactive. You can spit in them and they will react. All right, that's why it says that the reactions must be protected from moisture. All right, saponification, we've talked about this. This is just basically breaking down an ester group. All right, you're breaking down an ester. Again, hydrolysis of an ester. You're adding hydroxide to it. When you add base-catalyzed, it's called saponification. Okay. So here you go. You have a triglyceride, sodium hydroxide, to break them down into the fatty acids. Okay. Hydrolysis of amides. All right. Amides, either in the presence of acid, well, they do have base. Acid works really good. But you can see if you add acid, all right, to an amide, you're going to break that. Basically, you are substituting the ROH for an OH. Okay. Our skin are a bunch of amide bonds. That's why you don't want to get acid or base on your skin, because it starts breaking down the amide bonds. It starts hydrolyzing the amides of your skin or in your eyeball. That's why we wear goggles, because your eyeball is a very moist environment. So with that additional water, it actually breaks down amide bonds a lot easier and a lot quicker. Okay, that's why we wear goggles in class. So this is the chemistry of why we wear goggles. Here's base hydrolyzed. Okay, pretty straightforward. Again, hydroxide adds, kicks up, forms a tetrahedral intermediate. O- kicks down, your NH2 leaves, and then it deprotonates to form ammonia. Okay, similar to hydrolysis of esters, but instead you have a nitrogen. Here's the acid hydrolysis version. Again, guys, this is the same thing. This is very repetitive. Protonate, kicks up, tetrahedral intermediates, proton transfers, kicks down, kicks out your ammonia. Your ammonia deprotonates to form a carboxylic acid and the ammonium ion. Okay, these are the same thing. If I am going too fast for you, obviously you can watch these videos as much as you want, or we can just talk about these in class. So make sure that you bring questions. All right, hydrolysis of nitriles, we've seen this in class. We haven't really seen it stop though at the amide. Most cases we've seen it go straight to the carboxylic acid, but you can stop at the amide. The ways you do that is by putting in one equivalent of water rather than excess equivalent. Notice you're putting in one equivalent of water. Here you're putting in more water, or you add more base. You add two equivalents of base to it. Okay, so it just depends on how much base you're adding. If you add one equivalent, you can go from a nitrile to an amide. If you added more base, you can eventually go to the carboxylic acid. That's the hydrolysis. All right, Heating with aqueous acid and base will hydrolyze the nitrile to a carboxylic acid. Okay, also to an amide. Okay, so here, base-catalyzed of hydrolysis. All right, you see that enol tautomer of the amide. All right, you see that compound right here. Okay, what a tautomer is what can happen is these can pop down, and this goes up and grabs a hydrogen to form the amide. Okay, if you added more base in there, then you can break that down to the carboxylic acid. All right, reduction of esters to alcohols. How many times have we seen this, guys? This must be like the 4th chapter that we've seen this reaction. Okay, take an ester, LEH, all the way down to the alcohol. Nothing new. Here's the mechanism. Hydride attacks O-, tetrahedral intermediate, pops back down, kicks back out your RO group to form an aldehyde. Since you're an LEH, though, LEH does not stop at the aldehyde. It keeps going. You now have a second hydride come in. This time you don't have a leaving group. It just stops there. You add acid and it protonates. Okay. Now, when you add these weaker reducing agents, what actually happens is you stop at the aldehyde. Well, why do you stop at the aldehyde with these weaker reducing agents? Well, I'm going to show you. Okay. What happens is when the hydride attacks and kicks up to form the O-, the O- actually forms a very strong bond with the aluminum. Remember, LAH, the O- is a lithium, which is basically a very strong base. So that lithium is not really attracted that much of that minus, so the minus can pop down. This is almost like a covalent bond. I mean, it's not, it's ionic, but it's a much stronger bond than with the O- and the lithium. So because of that, it traps it in the tetrahedral intermediate. Okay, it freezes it in the tetrahedral intermediate. It does not pop back down and kick out the O or the RO group and keep hydriding. It stops here. And then as soon as you add acid, that's when this, or water, that's when it drops down and it kicks out the OR group. But in the presence of water, you no longer have any hydrides left. Okay, so you can't keep adding so LAH will then take this aldehyde and keep going to the alcohol, but we no longer have any more hydride, so we can't do it. Okay, so diisobutyl hydride, commonly called DIBAL, is another one opposed to the opposed to the other one, the chert butoxide one. All right, but it does basically the same thing. It stops and it doesn't keep going. That's the difference. Okay, so you can reduce amides to amines. Doesn't matter if it's primary, secondary, or tertiary. Okay, with LAH. Notice it's LAH. Same thing. Hydride goes in, tetrahedral intermediate, and you can kind of see what the mechanism is to form the iminium salt. This is a little different, but it's kind of similar. You can also hydrogenate as well, the nitriles. Organometallic reagents. You can take an ester or an acid chloride and add 2 equivalents of a strong nucleophile and do a double alkylation. Notice it's double alkylation. Let's look at the mechanism. Grignard adds in, kicks up the O-, pops back down, kicks out the RO group to form a ketone, and then the second equivalent adds to the ketone you just formed to stop it at the O-, and then you protonate with acid.